Hey everybody, this is Eric Wu. Today we're looking at problem 22 on the 2011 AMC10B. A pyramid has a square base with sides of length 1 and has lateral faces that are equilateral triangles. A cube is placed within the pyramid so that one face is on the base of the pyramid and its opposite face has all its edges on the lateral faces of the pyramid. What is the volume of this cube? The problem gives us a square pyramid with base length 1, so let's draw our square base. Square base kind of looks like this. We'll do a quick sketch since we won't actually solve the problem on the diagram. We'll have to draw a different one, but for now, this is sort of a square base. So this is 1, 1, 1, 1. And we have faces of equilateral triangles. So if the apex is here, it sort of looks like this. Let's erase this 1 since it might be confusing later. And it kind of looks like this and here. So this is our pyramid. It's just a general sketch. And we have another cube in this diagram. So let's draw it in red just to set it out. And the cube, the top face of the cube, the edges of the top face of the cube all lie on the faces. So basically the edges of the top face of the cube are making contact with the pyramid. So our segment is here. Let's just draw this segment over. Yep, so it looks like that. And it extends downward since it's a cube. So we have something like this, and this extends about to here. So this is just a quick sketch. This should be solid, and this is dotted. So we have our cube in this square pyramid. The faces are equilateral triangles here, so we know this is 1, 1, etc. Just drawing a few ones. And we have this cube in here. So how we'll approach this problem is, right now this diagram is really messy since I can't really draw. So it would be really difficult to solve the problem in this diagram since we'll have to draw some extra lines. So instead, we can take a 2D view of this, and how we'll do it is, let's use blue this time since it might start getting confusing soon if we use the same color. So let's look at this line here. It's a diagonal of the face, the base actually, not the face. So let's draw this over so it looks more realistic. The red should go over this. So now it looks like this is a diagonal of the base, which it is. That's how we drew it. And we'll look at this triangle here. Look, we take a look at this triangle here. Right here. This triangle, it consists of the diagonal of the base and these two edges of the face. So it's kind of like a plane bisected this pyramid in half. So drawing this triangle, actually let's do it in black. So we'll keep this here just as a reference guide, but what it looks like is, let's draw it down here. So we have this triangle. Actually, let's draw that better since it's an isosceles triangle. We don't need it that big, so let's just do it like this. Doesn't have to be perfect, it's just sketches. So we know that this is 1 and this is 1. We're just taking a 2D view of this, looking at this like bisection face sort of, and this. So we know that this is a square, so how we'll find the length of this is in the square. So the edge we use for this triangle is right here, 90, and we know this is 1 and 1. So by Pythagorean theorem, we have this is 1 squared plus 1 squared square root, which is just root 2. So we know that this length is root 2. Root 2, and erasing this now, and drawing in red now we'll draw how the cube looks from this 2D view. So we kind of have, let's do it in green now. We're using several colors now. But basically when we do this bisection of the pyramid, the cube is also bisected right here and right here. So basically all we can see is this rectangle now. So let's draw the rectangle here. The rectangle kind of looks like this. Keep in mind this might not to be scale based on what the side length of the cube is, because we don't know what that side length is. That's what we're trying to find. But now actually we're trying to find the volume, but we need the side for that, but yeah. And so let's call the side length of the cube S. We're trying to find S cubed, since that's the volume of the cube. Find S cubed. Drew an extra line there. So to find what S cubed is, we'll need S. And looking at this diagram, we know that this is S and S, the way we bisected it, and this. So looking at the top face of the cube, this is a square. We have this is S and this is S, and we used this length for here. This green length is this length. And by Pythagorean theorem, we have this as S squared plus S squared square root, which is S root 2. So this is S root 2. Erasing all of this, since we didn't need that either. So how we'll solve this now is looking at this 2D view. We know that this is 90, 45, and 45. And this is true because we have two side lengths of 1 and one side length of root 2. And 1 square plus 1 square square root equals root 2. So since Pythagorean theorem holds here, that means this has to be a right angle. But since this is 1 and 1, that means this right triangle is also isosceles. So the sum of this angle and this angle equals 90, since we used one 90-degree angle. But since they have equal values, that means it has to be 45 and 45. So now we know these two angles. We know these are 90, since this is a rectangle, which in turn means this angle is 90, and this angle is 90. Now, since we know this is 90 and this is 45, that means this angle here has to be 180 minus 90 minus 45, since the sum of these three angles is 180. And this in turn means 45 degrees, so that means this angle is also 45 degrees. And similarly, this is 45, since these two are congruent triangles. Now, since we have two 45-degree angles, we know that this triangle is isosceles, so this has to be S. This has to be S, since these two lengths are equal, since they're isosceles. And since we know this side of the rectangle is S root 2, that means this is also S root 2. So now we have an expression in terms of S. We have S plus S root 2 plus S equals root 2. Erasing this, we're almost done with the problem. S plus S root 2 plus S equals root 2. So let's factor out the S. We have S times 1 plus root 2 plus 1 equals root 2. S times 2 plus root 2 equals root 2. S equals root 2 over 2 plus root 2. Rationalizing this denominator gives us S equals root 2 times 2 minus root 2 over 2. So we have S equals, well actually let's just make some more space. So let's erase all of this, we don't need that anymore. And we'll draw an arrow. S equals 2 root 2 minus 2 over 2. We distributed the root 2. And dividing by 2, we finally have that S equals root 2 minus 1. So the only thing remaining is to find the volume of this cube now that we know the side length, which is S cubed. Erasing this, we have what S equals to, so we don't need that anymore. And by binomial theorem, we have A minus B cubed equals A cubed minus 3A squared B plus 3AB squared minus b cubed. So plugging in a equals root 2 and b equals 1, we have root 2 cubed minus 3 root 2 squared times 1 plus 3 times root 2 times 1 squared minus 1 cubed. And expanding all these and simplifying, let's erase this. We don't need this. This is our final expression. Drawing arrow again, since this is taking a lot of work. Root 2 cubed is 2 root 2 minus 3 times root 2 squared, which is 2. So 3 times 2 is 6. Plus 3 times root 2 minus 1. Which, combining similar terms, gives us 5 root 2 minus 7. So our answer is 5 root 2 minus 7 for the volume of this cube here, which is answer choice A. Now we solved problem 22 on the 2011 AMC10B. I'll see you guys next time.